So next up, we have Michel Rieutord. He's a professor of physics and astrophysics at Paul Sabatier Toulouse III University. He's a specialist in astrophysical fluid dynamics. He has a special interest in rotating fluids. And in the last few years, he and his team have been developing two-dimensional models of fast rotating stars. And also Michel is leading the ESTER project about fast rotating stars. So yeah, I'm very happy that he's here to talk, and he's going to talk today about why we should care about waves in stars. So thank you, Michel.
So yes, I will talk about waves in stars, and the question is why should we care about waves in stars? The answer is yes, we have to care because the waves are really giving us a lot of information on stars. So in these 3 lectures, I will talk about the evidences that I would say, of the presence of waves in stars. And then I will be back to basics and teach you a little bit about waves and some waves. In fact, what is a bit difficult with waves. Then just review the zoo of waves, and I think I will miss some of them because it's too much time to be exhaustive. And then finish with the, I would say, the most difficult, which is all the nonlinear effects that are associated with waves, and namely the transport of momentum and chemicals, and then finish with some conclusion. That will be on Friday. So to start with, let us see what the stars are teaching us about waves, and can we see waves on stars? And so that's the first question, and I will show you that yes, we see indeed waves on stars. And I would like to show you first this a little video that I made with the image which are taken by this by the TESS satellites, which is dedicated to the detection of exoplanets around stars by the transit mean. And since this satellite is observing the whole sky, then we have a lot of variable stars in the field of view. And one of these variable stars is the leader of the Cepheid stars. This is Delta Cephei, and I just grasped or downloaded the data about the field of this star, and I will show you this if it works. So first, I should stop. So I think you don't see anything for the moment, but I will, so I have to stop share and share again with the video. Okay, can you see the video?
Yep.
Yes.
Yes. Okay. Good. So I run it. So in the middle, so I should first explain. You see many stars as viewed with the TESS satellite. So the pixel is quite big. It's 20 arc-second. So and in the middle you have this bright star, which is the leader of the Cepheids, and which is saturating actually the receiver, the target, the CCD. Yes. And so let's go. Let's run. So what you see first is that the luminosity. So let me start again with the beginning. So you see it's some fluctuation, in fact, in the just outside the star, and you see the luminosity is growing, and you see these spikes which are growing. In fact, these are the electrons. I mean the wells which are filled by the growing luminosity. In fact, in the whole video is 27 days, so the time is passing quite fast. And again, you see the star is dimming, and then whoop, it grows quite quickly, and then dimming again slowly. So, and this is typical of these stars. So let's see it again. So we see a slow dimming and then rapid growth now, and then slow dimming again. And then we pass, so the satellite is coming close to the Earth. So the whole thing is dimming, you see, the whole stars are dimming, and then back again. You see the growth of the luminosity of the Cepheid, and then it's slow decrease, and again and again. And you can see also at this place, you see this little star which is just flashing. This is another star. I don't know what's the reason of this. It could be, you see it's here, it's just oscillating, so it might be also the signature of waves. So I stop here. Okay, so let me go back to the slides. So other stars which more classical things, I show you this light curve. This is, you see an eclipsing binary with the primary eclipse, the secondary eclipse. But what I would like to see you is these little wiggles on the light curve. And if we take the Fourier transform of it, then we see that there is a nice peak here at a frequency of 5.4 millihertz, which means a period of 180 seconds, so 3 minutes period. So that's quite short. And in fact, this is betraying some acoustic modes in this star. And so if we are able to identify this oscillation, or to which mode is it corresponds, then we can have information on the acoustic properties of these stars. It means on the sound velocity. More classically, with light curves of the test satellite, you see something like this. And when you take the Fourier transform, you see many modes, and the same game is to identify these frequencies and then to derive some physical properties of these stars. I would like to spend some time on Altair. Altair is a bright star of the summer sky, at least in the northern hemisphere. And this is a star which has the peculiarity of being quite near us. It's 5 parsecs away from the Earth. And it has been the target of a lot of interferometric observations. And from these interferometric observations, people have been able to determine its shape and show its inclination with the line of sight. And I show here a model on the right, which has been computed precisely with this, with the 2D Esther models that we are running in Toulouse. And so on this model, you can see that the pole is brighter than the equator, and this is a feature of rapidly rotating stars. This is a simple consequence of the fact that the pole is closer to the center than the equator. And if you just imagine that the heat flux is inversely proportional to the distance, so you see at the center you have a sort of 20 million degrees, at the surface you have 0. So the temperature gradient is higher towards the pole than towards the equator. And so the heat flux is stronger along the pole than along the equator. And that makes these stars with a bright pole and a dark equator. And this is very useful to get the orientation of the star in space. So that was a preliminary, but then we observed this star at Pic du Midi in spectroscopy, And I wanted to see waves propagating on these stars. And then I show you what we have seen is this. So I should explain. So the waves are here. Can you see my arrow? So these are here. But first, let me explain how we got this this sort of wavy drawing or picture. So the first thing is to, when you get a spectrum of this star, then you try to get the average line profile of a single spectrum. So during a night, and you see the night lasted 6 hours, and we got hundreds of spectra. And for each spectra, we get the mean profile of all the lines that are visible on one spectrum. And then I take the average of all these mean profiles. And I think this is this average. And then I subtract all this average to all the mean profiles. And then I can get these wiggles that you see here, brighter, darker, like this, along this blue line, for instance. And then I pile up everything, all these departures from the mean profile on the vertical axis. And so I see this, and I see, what do I see? Well, in fact, as you can see here, the abscissa here is given in kilometers per second. So in fact, what you have also here is the longitude of the star, actually. So in fact, the minus 200 here, this is the blue side of the star. So I would say the eastern star, yes, maybe well, not really. So the blue side of the star, the side which is coming toward us, and which is blue shifted, Doppler blue shifted. And along this mean profile, you have little wiggles that are propagating along the profile, and so along the azimuth of the star. And this is what you see. So you really see waves propagating on the visible side of the star. So what we can do when we see waves, well, the first reflex to have is to say, oh, I can take the Fourier transform of these of this signal, either in time, either in space, because here I have 2 dimensions. So the first thing I did was to take the Fourier transform, or the Lambskargel transform, along this blue line. So just to cut this and see what is the spatial frequency of this wave, and try to identify this dependence with the longitude. And so you see that as time passes, you can have, say, m equal 10 or m equal 12, and then 2 waves with different m at 3 hours, and then again a single wave. So because you have some beating process, or yes, superposition of waves, and you see that what is giving these patterns is precisely, most probably, these waves which are propagating in longitude, and you see that they are propagating in the sense of rotation. So they are prograde waves. You see that they go from the blue side to the red side. So the blue side is coming towards you, and the red side away from you. So they are prograde waves. What you can see also is you can do a sort of time frequency analysis. So at each time, yes, you do a Fourier transform. Oh, so what? Sorry, what did I do? No, for some yes, for some time slot, then you do a Fourier transform in time and see which frequency, which time frequency is excited. And what you see is that around 3 hours, you have a mode with a frequency of 40 cycles a day. Per day, so that means a period of a bit less, yes, less than an hour. Half an hour would be 48, so it's between half an hour and an hour, typically the periods that we are seeing here. So maybe these are most probably gravity waves which propagate at the surface of the star. So this is a premiere. I haven't published yet these data, so it's going to be that I haven't had time. These were obtained in September, last September. So another star where we will see waves is the Sun, but I think I will let Aaron speaking about that, because of course on the Sun we see the surface and we can have a detailed look at these at its waves. I have just for the sake of the beauty of this film, I would like to show you the alpha waves in the Sun's atmosphere since, so here it is. I hope you can see it. So you see the atmosphere of the Sun, and what you can see here is these loops of which are featured by the magnetic field in the atmosphere, and you see along these loops some perturbation of the brightness in some special wavelength, some perturbation propagating along the magnetic field. So I won't say these are surely alpha waves. They can be magneto-acoustic waves. There are all kinds of waves when you put magnetic fields, but here, since it's dominated by magnetic fields, you can expect alpha waves or magneto-acoustic waves, so the combination of acoustic waves and magnetic waves, so to speak. So let me finish the film just for the fun. So you see that, in fact, these waves are also quite important in the sense that we attribute to them the property, which is not yet demonstrated, but the property of heating the corona. But it's a good candidate, but I don't know, as far as I know, it's not proved yet, although we have good reason for thinking these are very useful waves. So let's stop this sharing and go back to the slides again. Where are they? I'm sorry. Where are the slides? Should quit this? Yes, so they are here. Okay. So so waves are in fact expected in stars, and why they are expected, just from the idea we have of stars, since you know in stars you have a lot of turbulence, especially in the convective envelope or in the convective core, and turbulence, as usual, makes noise, and thus it must excite acoustic waves, and actually this is seen on the Sun. Another way to excite waves is that these convection zones, they are either below or above a radiative layer, which is stably stratified, and so where you might have gravity waves. And so when the plumes, the cold plumes, for instance, from a convective envelope hit these stably stratified layers, then they will excite gravity waves and or inertial waves, which are the waves associated with the Coriolis force. I would like to see you another video which comes from the laboratory, and where we see internal gravity waves. These waves are quite difficult to see, and so it's nice when you have an experiment which shows them. So again, I have to change the sharing. So I run it. So first I should explain what you see. So in this container, which is illuminated by a laser sheet, so you have at the bottom here a heavy fluid, which is SF6, so hexafluoride of sulfur, or sulfur hexafluoride. So this is a very heavy gas, 5 times heavier than air. And here you have air with some smoke or some trace just to see its motion. So my colleague, in fact, has filled, so the container was filled with air with this smoke, and it has filled it with some SF6 in the bottom, and so this has pushed air, and you see here some interface. And now we shall excite. So this is a really stably stratified situation. You will see that this is very strongly stratified. And so you see that my colleague is blowing some air into this system, and you see at the interface here these waves, and these are internal gravity waves, which are just due to the strong stratification. And if you want to destabilize this, you have to blow quite hard, as he will do. You see? And so you see here mixing with, so a mixing which is due to the turbulence that is generated because of the shear, because he's blowing quite strongly. And you see that everything is resisting to that. Well, it's there is some mixing, and of course some of the SF6 is mixed with the air, but you see that there is still strong stratification, and the thing is still oscillating, and when it oscillates, it doesn't mix actually. So I will come back to this problem of mixing by waves and transport by waves in the last lecture. But what I would like you to remember is that using wave to mix fluid is a hard business. In fact, waves are not very efficient, at least on the short term. So I just finish again the video. So yeah, and in fact, this is an experiment that we have built in Marseille, and to study precisely the mixing between the convective core of massive stars and their envelope, which is stably stratified. So that's the reason. This was the first qualitative experiment just to see how it works. So I stop here. Okay, so and what we have seen, the last point was, of course, that the convective envelope can excite Alphen wave in the stellar atmosphere, like in the sun, and Matt has talked about that, and so I won't dwell on it. So just come back to the shock waves in the stellar atmosphere. In fact, so what I show here is the light curve of delta Cepheid, so the leader of Cepheid stars, and you see this fast rise that we see on in the video, and then the slow decay, and then again the fast rise and the slow decays. And in fact, this is explained by shock waves which propagate in the atmosphere of the star. And these shock waves are actually the acoustic waves which are breaking in the atmosphere and which are giving many features actually in the spectrum and on the light curve of these stars. And this is, of course, this is not only the case of Cepheids, but also the case of RR Lyrae stars, of beta Cepheid stars. I would say rather massive stars, at least the beta Cepheid and the Cepheids. And why people have thought these are shock waves, in fact, it's because when they look at their spectra, they can see emission lines. And so you see in the spectra of stars, what you usually see is absorption lines. But if you, by some mean, you can excite the layers, you can deposit energy, then you will see emission lines. And what you see here, for instance, on these lines of hydrogen, is that this line is actually oscillating in with the Doppler effect, meaning that in fact the position where it is forming is just moving up and down, or yes, up and down. I'm extrapolating. In fact, it's moving with high velocity, low velocity, and this just betrays the motion of the atmosphere. This has been simulated now for quite some time, and one of the experts is Denis Gillet, who has computed these, the propagation of these acoustic waves in the atmosphere and shown that they generate shock waves that you can see here as time passes. And that was for an RR Lyrae, but this is the same for Cepheids, and maybe you have many modes. Well, this is quite a complicated business, because these shock waves are isothermal shock waves and not quite the same as the one that we experiment in the lab here on Earth. Another fascinating phenomenon, and which has excited a lot of the the astrophysicists, is this QBO, these quasi-biennial oscillations that is observed in the stratosphere of the Earth. And this is a performance of gravity waves which are generated by the troposphere in the stratosphere of the Earth. And I would like to comment on this diagram, because I will come back on this process, I think, in my last lecture. So this is a phenomenon. So let me describe what we see here. So in abscissa, you see the time passing in years, and in ordinate, this is the pressure. So this is the height, and this is the in fact, a layer which is roughly in between 20 kilometers and 30 kilometers in the Earth's atmosphere. So this is rather right in the middle of the stratosphere. And what you see is that, for instance, if you consider a given height, so you are blue, then red, and then orange, blue, orange. And there is this alternating feature. So blue is negative velocity, which means, I think, westward wind. And the orange one is eastward wind, is prograde. And you see that, so there is a wind which oscillates with a period which is about 2.5 years. And this wind, in fact, has the special feature that it's almost at some time, it's almost occupying the whole layer. So the whole layer is moving to the west, and then 1.5 years later is all moving to the east and back. And so this is a very surprising behavior, actually. And this was discovered in the 50s, in the 1950s, and The explanation of that was given in the 1970s, actually, so 20 years after. And I would say the explanation of that is because in the stratosphere you have you can support gravity waves, and these gravity waves actually deposit their momentum, so their linear momentum toward east or toward west. And as time passes, so I should explain well what's going on, in fact. So just consider, for instance, the situation in 1982. So you see that the flow is moving to the west. And in that case, I will show you that waves which are propagating to the west, they are absorbed by this layer, in fact, by a layer which is moving in the same direction of that. In fact, they have a wave number which is higher, and they dissipate in this. So when they dissipate, they deposit their momentum. And so the layer, in fact, is extending. But for the waves which are propagating to the east, this region, this blue region, is just transparent. So they just go through, and they go through to the top, in fact, to a region where they dissipate. They cannot do anything else because the conductivity or the diffusivity is high in this region. So they dissipate, and they, in any case, they deposit the momentum. So they can cross and they deposit the momentum, while the westward waves, they are stopped here in the blue region, and they cannot go to the top. So there is only the eastward propagating waves, which goes to the top and deposit the momentum. So this layer starts to accumulate momentum from these eastward propagating waves, and so have a sort of bulk force which push this layer to the east. And so as this layer develops, the eastward propagating waves are more and more absorbed by this layer, and this layer extends with time to the bottom. And as it covers the whole layer, then this layer becomes transparent to the westward propagating waves. And so the cycle repeats, and you have this alternating oscillations of this layer. So I mentioned this because this phenomenon has sort of excited the astrophysicists, and many people have tried to reproduce this in stars, because in stars you have also a region of stable stratification where you can have gravity waves, which is in contact with a convective region where you have a flow, turbulent flow, which can excite the waves. And so why not? Why wouldn't we have such thing? And I would like to show you this last video, which was computed by the group of Daniel Lecture1 in Princeton, and where we can see in fact the waves, the gravity waves, making their own critical layer and just generating some shear layer, actually. So let's go and see this layer, this film, if I can. Yes. So, and let's run it. So you see these gravity waves propagating to the right, and so these are the three components of the velocity. So the most spectacular one is the ux velocity. In fact, here you have a layer which is flowing faster than here. You can see that waves propagate faster. And so when these rightward propagating waves come into this layer, they dissipate and they deposit their momentum, and you see that they generate a strong shear layer, which is so strong that it generates even turbulence at the interface. And so that's an interesting process if you are interested in the mixing by such waves. Of course, then you need some sorts of waves to generate this, but I guess these simulations are for the exploration of this mechanism, and I can tell you that this is not fully understood. There are a lot of surprises that will be discovered. So that's, I think, my last film, and then now I will stop and go back to the slides. So I'll stop sharing, and back to the slides. Up, up. Okay, so just to summarize, I think, I hope I have convinced you that we can see waves on the surface of stars. Actually, I have shown you on one star, but I can tell you there are other stars where we see the same thing. We can monitor their impact on the brightness and on the spectra of stars. That's yes, that's for sure. And one question we have about them is that, we suspect that they have a strong, some influence. I don't know if it is strong, but they have some influence on the dynamics, on the internal dynamics of stars, because they can, as I've shown you, they can carry momentum, they can carry chemicals. And so when you are measuring the abundances on the surface of a star, or you are measuring the differential rotation at the surface of a star or in the star, then you have to know what are all the sources of chemicals. I mean, the way they are transported, and the way momentum, angular momentum especially, is transported. So the conclusion is that waves need to be studied, that's for sure. So the next step now is to go into the study of these beasts. And I will go, rather to the basics, and maybe some subject which is not so basic, but you will tell me. So, in fact, the basic problem is to study the perturbations or the disturbances on a background which you know, and derive all the quantities that can be obtained from the measurement of, for instance, the frequencies or the amplitudes of the waves, etc. So the basic problem is, what can we say about perturbation on a fluid flow? So to make the thing simple, I will most of the time consider an incompressible fluid, maybe inviscid, but for sure incompressible, except of course when I'm talking about acoustic waves. So what are disturbances? So let's consider a steady flow, which is driven by some force, some bulk force, which verifies Navier-Stokes equation, and so the mass conservation, which is just the divergence of V equals 0, and meeting some boundary conditions on some boundary. So here I use the no-slip boundary conditions, but it's not a point. So then you perturb this solution of the fluid equations, and of course the disturbed flow is also verifying these equations. So the V plus delta V should be also a solution of Navier-Stokes equation, of the mass conservation, and of the boundary conditions. But of course, you know that the original flow is verifying these equation, and so you can subtract this equation to this equation and derive an equation for the perturbations. This is what I have done here. And what you see immediately is that the perturbations do not verify the same equation as the original flow. You have these new terms, which is V grad delta V or delta V grad V. And of course, this is these two terms, they just mean that this flow, the perturbation depend on the original flow. So, and this you can see comes from the fact that the equations are non-linear. If they were linear, then the perturbation would verify the same equations as the linear equations. So this is the charm of these perturbation equations, that they are different when you study different flows. So there are two ways now of simplifying these things. In fact, these equations are very complicated, so we have to simplify. And to make progress, the first thing is to say, okay, I will consider very small amplitude perturbations, and basically noise. You know, the fluid is made of molecules, of atoms, and there is always Brownian motion in the fluid. And so this is always making small perturbations. And if the perturbations are very small, then the nonlinear term, like these ones, are negligible, because these are of amplitude epsilon square. Of course, if you consider perturbations which are strong, which are of finite amplitude, then you have to consider these nonlinear terms, and this makes the problem much more complicated. So the first step is to consider vanishingly small amplitude perturbations. So I just dismiss the nonlinear term. I'm still sticking with this. And I would like to simplify this again by considering only plane waves. When I do that, the nice thing is that I impose the spatial structure of the waves. I assume that these are just a sinusoidal oscillation as function of the spatial coordinate. And I also assume that the temporal dependence is also periodic. So when I do that, in fact, I just have as unknowns these quantities, the amplitudes, which are constants. All the operator, they just transform so into multiplications, sorry. And you get these kinds of equations which relate the amplitudes, and which are, of course, function of the background field. Of course, when I do that, I'm authorized to do that only if this background field, in fact, the velocity gradient or the velocity itself is a constant. I will come back on that. And one thing you can note also is that the divergence of V equals 0, so mass conservation, imposes that the waves are transverse, so that the velocity is perpendicular to the wave vector. So you can then rewrite these two equations, actually, into a matrix or a linear system that I have written here. Some fourfold matrix applied to the three components of the velocity and the perturbation of the pressure. Of course, since the solution must not be zero, then it means that the determinant is zero, and the determinant of this matrix, and this gives you the famous dispersion relation, which is an implicit relation in the general case between omega, so the frequency of the wave, and the wave number. And that means that when you solve this equation, then you may have many branches. And I will immediately show you an example of that. I just consider, for instance, a gravity wave which is propagating at the surface of water. I assume that the air which is above the water is flowing at some velocity, some constant velocity, and that the water below is just at rest. And you have, of course, waves, but so I consider these waves, and you can derive the dispersion relation of these waves. I skipped this a bit complicated or tedious calculation, and you get something like this. So this is a polynomial relation between omega. You see that omega is squared, omega, so this is a second order polynomial in omega, but this is also a third order polynomial in the wave number. So you may solve this equation for solution in the frequency, in omega, or in the spatial frequency, and so you will have either a third order equation or a second order equation, a second order polynomial. Fine. So you have actually 2 temporal branches or 3 spatial branches. I will concentrate on the temporal branches, which is easier to understand. So in this problem, I have a parameter which is the velocity, the speed of air above the water, so the speed of wind. And if the speed is low, then you have 2 branches like this. And in fact, these are 2 complex conjugate roots of this problem. But since, so this is the Kelvin-Helmholtz problem. In fact, if you increase the velocity of air at some, when you reach some critical velocity, then you see that the branches are getting into contact. And when you go over this critical velocity, you see that the dispersion relations, in fact, has no longer real roots in some band of wave numbers. And in this case, in fact, the flow is unstable. And this is actually the Kelvin-Helmholtz instability. One thing I should say about this, this way of presenting the Kelvin-Helmholtz instability is that when you look at these branches, this branch, you see that the omega changes sign in some region here. And in fact, you can assign to this branch an energy to the waves. And in fact, this branch is associated with negative energy, which is defined in some wave. In fact, it's related to the derivative of the dispersion relation. So this wave actually is of negative energy, while this one is of positive energy. And so when the 2 waves interact for these wave numbers, in fact, they can exchange energy, and the whole system can keep constant energy, while the 2 waves can have amplitude which goes to infinity, which means that, in fact, in this case, you have an instability. So in fact, the waves are pumping energy into the flow and growing exponentially. So I close the parenthesis now. So let's do another problem about acoustic waves, which can also be unstable. And I show here a very classical example of an instability which is affecting acoustic waves. And this is the gravitational collapse. So just consider these waves. So you recognize here mass conservation. And this is the perturbed equation. So you have perturbation in density and in velocity. So the fluid is at rest, constant density, constant pressure. So waves can propagate. And if you just concentrate on this, if you forget about the gravitational potential, then you get just the classical acoustic waves. But if you add the perturbation of the gravitational potential, so delta phi here, this delta phi is driven by the perturbation of density. You know, this is Poisson equation. And what happens if you derive the dispersion relation of waves taking into account the perturbation of the gravitational potential, you get this dispersion relation. And you see that gravity comes in with this new term here, which is negative. And you see that, well, if this term doesn't exist, then you have the usual dispersion relation of acoustic waves. But if you add this physical phenomenon, then you see that for some wave numbers which are lower than some critical wave number, then you have imaginary frequencies, which means that you have an instability. And this is the gravitational collapse, actually. And you see that it depends on this wave number, actually. So it affects the small wave number, so large wavelengths. And this is called the Jeans wavelength, or the Jeans length. And for wavelengths which are larger than this Jeans length, the acoustic waves are unstable and they grow exponentially. What I usually do with students is that I compute this Jeans length in the Earth atmosphere, and what we find is that this wavelength is about 70,000 kilometers. So it's a bit large compared to the size of the atmosphere. So there is no problem for the Earth atmosphere to collapse. But if you apply this to a molecular cloud in the galaxy, you find that this wavelength is typically a few parsecs, while the size of the molecular clouds is usually a few tens of parsecs. So in fact, you have these clouds are unstable with respect to the gravitational collapse. So of course, this is a local analysis. And when I did that, I assumed that the background was uniform. In fact, with this, I cannot deal with boundary conditions. In fact, I assumed what I said, that the wavelength is much smaller than the scales of the background. And in particular, for instance, the scale of velocity must be much larger than the wavelength. So if this condition is not met, then you are done. You cannot use the local analysis, and you have to take into account these variation of the background and all the boundary conditions which will select your wavelength, for instance. So maybe I should stop here. I see that time is gone for me. So tomorrow I will continue on this more complicated problem where we have to deal with the boundary conditions. So thank you for listening.